So today we're going to do our second unit on uncertainty. And we're going to talk about uncertainty today in the context of regression. So last time we talked about uncertainty generally in terms of how we could compute standard errors, in terms of how we should think about sampling distributions, how we could think about uncertainty in parameters that we're estimating from a statistical distribution. So we can think about how we could take a sample and how we could take the variance of our sample along with the mean of our sample, use the central limit theorem, and compute a standard error and a confidence interval, assuming that the distribution of our sampling distribution for the statistic we're interested in is approximately normal, right? So we make this assumption that if we were to repeat this experiment many times, we know that on average, X bar, or the mean, the sample mean, would be distributed approximately normal, right? And so we can use that to then approximate what that normal distribution may look like and compute an interval that could describe our uncertainty. Yeah. So we're going to extend that logic to the case of regression now. So let's just kind of briefly review the linear regression model. We can describe the relationship between a predictor value X and an outcome variable Y with the line Y sub I equals beta 0 plus beta 1 xi plus epsilon I, right? We're familiar with this. We're kind of an intercept, a slope, and an error term. Lets us model Y as a linear function of X. So beta 0 is the intercept. That is, it's the value of Y when X is equal to 0. So when X is set equal to 0, Y is equal to beta 0 plus epsilon, right? Beta 1 is the average increase in Y when X increases by 1 unit. How much does Y go up when X goes up by 1? That's a slope. Epsilon is the distance between the line Y equals beta 0 plus beta 1x and the observed values of Y. Right? So we typically will say Y hat or Y predicted equals beta 0 plus beta 1x. And so beta 0 plus beta 1x differs from the true value of Y by some amount, and we call that amount the error term. So the expected value of yi is equal to beta 0 plus beta 1 xi. That is, our best guess for the location of y is equal to beta 0 plus beta 1 times x. That's going to fall exactly on the regression line, right? But the truth is the values of y we observe are usually not exactly on the regression line, right? So our predictions almost always have error. So some notation. We put a hat, a little triangle on variables to indicate that they're estimated or predicted, right? These are not the observed values. These are the estimated or predicted values. So actually in regression, what we're after is beta 0 and beta 1, but what we're really computing is beta hat 0 and beta hat 1, right? There is some hypothetically true linear relationship that relates the variables x and y, but we only have a sample of x and y. We do not have all of the possible values of x and y. So what we're computing is one possible value of beta 0 and one possible value of beta 1. How do you think we're going to characterize the set of values that beta 0 and beta 1 could come from? We're going to characterize them as sampling distributions that follow an approximately normal distribution, just like we did with X bar, right? So we're going to use the central limit theorem to say, under repeated analyses, that is, if we took repeat samples and computed lots and lots of values of beta 0 and beta 1 for some y and some x, we would get a range of possible beta 0s and a range of possible beta 1s. Those can be described crudely as following the normal distribution. If we have an infinite number of resamples, they will follow exactly a normal distribution. And we can use that information to describe how certain we are about our estimates of beta 0 and beta 1. But what we ever actually get is a beta hat 1 and a beta hat 0. Beta 1 is an unknown parameter. We don't know it, but we're going to make a guess about its location from our observed data. Yeah? So there's some true parameter out there in theory that relates y and x as a linear function, but we don't observe all of y and x. So the best we can do is make a guess based on the data. And we're going to call that beta hat. So we're going to get predicted values of y hat, from our beta 0 and beta 1 hat that we estimate from the data. Yeah? Okay. So the residual, we can reformulate it as y minus y hat, or y minus the expected value of y. Right? So the error term is the true value of y minus our prediction from the regression equation for y. So let's think about this regression line for a second. Assume that beta hat 0 is 0.05, beta hat 1 is 0.95. Let's estimate y hat for each of these 10 rows. Just use R as a calculator or use another calculator to compute y hat. And you only really need one of these columns to do that. Y hat equals beta hat 0 plus beta 1 hat x, we'll call it y hat 1. In this case, we'll get y hat 1 equals 0.05 plus 0.95 times x1 is 0.342. That is y hat 1. And we can do that all the way down. So once we have this regression equation and our vector of x values, we can produce predicted values for every single y. If we have values for our betas and our x's, and we know the form of the regression equation, we can produce our expected values of y. That's all we need for prediction. So in this case, it's just 0.05 plus 0.95 times 0.342 for y hat 1. Now, what number is that? Anyone? What's that? 0.0342? So now let's take that and compute sigma 1. How would we do that? How would we compute our error term for row 1? Y minus y hat. Right? So it's 0.123 minus 0.3. That's it. So really simple arithmetic can get us all the way through this, right? So anytime anyone asks you to make a prediction from a regression equation, even though that sounds like something really complicated, it's not, right? Once we have our equation, all we need is this. All we need is our vector of x values and our betas. Once we have that, we can predict. So here's our regression line. These are the 10 data points I just showed you, just as a scatter plot, x by y. And I've set beta 0 and beta 1 in simulation to be equal to 0.05 and 0.95. That's okay. Here's our fit line. Here's what an intercept of 0.05 on the y-axis looks like, right? We're at y equals 0.05 right here. We have a slope where y increases by 0.95 for every 1 unit increase in x. So if we have an intercept of 0.05 and a slope of 0.95, when x equals 1, y should also be equal to 1. And it is. Okay, so this is the best fit line. And how does a regression line work? What is the best fit line? What does it mean for a line to be best fit? Yeah, it minimizes the sum of squares of the residuals, right? It has the minimum absolute distance between the line and all the points. We call it ordinary least squares for that reason. The reason it's the best fit line is that it has the least absolute distance between each of these points and the line of all possible lines, right? We can imagine a line that goes like this, but that would have more error. We can imagine a line that goes like this. That would have more error. This line, of the infinite possible lines, has the least amount of error for these 10 points. Least amount of absolute error, right? Once we square it.
You say that it seems like that's pretty common to use. Would you say that's the most common ordinary least squares regression?
Ordinary least squares is by far the most common analytic tool across the social sciences, yes. And a lot of the natural sciences too. Yeah. Hands down, the most common. Here's y hat. So our values of y hat, by definition, fall exactly on the regression line, right? Because it's just beta 0 plus beta 1 times x. So we're going to get values that fall exactly on that line, y equals beta 0 plus beta 1 times x, for each of our values of x. These are our expected values of y. And in most of the cases, these guesses are not bad, right? They're not terribly far away from the real values. The dotted lines indicate our errors. So these are kind of the components that go into a regression model and the kind of sets of values that we might be asked to think about from the regression model. Our observed values, our predicted values or expected values, and our residuals or errors. Right? Residuals and errors mean the same thing. Predicted and expected values also mean the same thing. Clear on this? This is review. I just want to make sure. Okay, cool. So now we're going to get into new stuff. Typically, our goal in linear regression, we can have a couple goals. A common goal in linear regression is to estimate a causal relationship between some predictor variable x and some outcome variable y, or some dependent variable y and some independent variable x. We might also, though, if we're not interested in a causal relationship, we might also be interested in predicting changes in some outcome y for changes in a system of predictors x. Both are reasonable applications of regression models. We can use them for causal inference if we design for causal inference, or we can use them to construct predictive models. Both are useful. So let's talk about the causal framework first. For estimates of beta to be unbiased and consistent. So when we're in a causal model, typically what we're after is an unbiased and consistent estimator of beta 1, right? Because what we're after in a causal model is what is the effect of x on y? And we can think about what we're after. But what we're really after is not beta hat 1. What we're really after is beta 1. But we're going to get a single estimate of beta hat 1. Right? We're going to use this to make an inference about this, which we can call the effect of x on y for a 1 unit increase in x. That's what we're after typically in a causal inference system. Now, what do we mean by saying something's unbiased and consistent? What does it mean for something to be unbiased? What is bias? Exactly.
Anything that would throw off.
Well, yeah, but what does that mean in terms of statistics, right? The average of the errors is not equal to 0. When the average of our errors is not equal to 0, our data is biased. That is, if the average error is positive or negative, our data is biased in one direction or another. So if we generate estimates that are too high or too low, if we generate predictions that are too high or too low, our model is biased. And consistent means that it follows the central limit theorem appropriately, right? Consistent means that it will converge to a normal distribution as the number of samples increases. So it'll follow, we'll be able to make, first things first, we want to make sure that our predictions of y, we want to make sure that y hat I equals y, which we can think about this as the average which could be equal to 0. The average of the errors, right? Another way to write this is the sum of epsilon that the average value of the error term should be equal to 0. That is, the positives and negatives should cancel each other out, right? We want to guess on the positive direction incorrectly as often as we guess in the negative direction incorrectly.
I know this is crazy, but if you like, you don't want to put live just talk about B, like beta, they're probably referring to.
Or yeah. I'll tell you more about that in a second. Okay. So we can describe that as a vector. We could describe, in theory, we could rewrite this regression equation as y equals beta hat will stand in as a vector for beta 0 and beta 1. We can use basically matrix multiplication to rewrite it this way. And that can be a way we can compactly write the regression equation for any number of x predictors.
Okay, so people included like beta is one of the table.
I'd have to see it, but typically they're going to be pointing to a causal, a parameter that their focal parameter, the thing that they're really interested in, the primary relationship. And then everything else might be described as controls, right? Okay, so we have to have a couple assumptions for beta, for our estimate of beta, for beta hat to be unbiased. That means our estimate of beta hat is not systematically higher or lower than the true value of beta, right? And for it to be consistent, that means it converges to the true value of beta as our sample size increases following the central limit theorem, right? Okay, so for those two things, the linear model must approximate the data generating process. This sounds kind of funky, but all this means is that the true relationship between y and x must follow a line, right? That is, x and y must be related to each other in a linear fashion. We'll talk more about what this means in a little bit. But that's a strong assumption, right? Think about the spread of a virus. Does that follow a linear pattern? No, it follows an exponential pattern, right? Because each individual doesn't just pass it to one other individual, they pass it to anyone they have contact with. So we see an exponential process rather than a linear process. So the linear process has to fit the real world data generating process. When I say data generating process, I just mean the thing that produces the data that we're analyzing. That's usually a real world process mediated by a survey or a sensor or whatever it is we're using to gather the data. So the data generating process is both like the thing in the world that makes the data, that makes the process happen, and then whatever we use to record the data itself, right? This is a funky one, but follow with me. Exogeneity of errors. So, anyone know what exogenous means? You may hear the terms exogenous and endogenous in statistical parlance. Exogenous means outside of the system. Endogenous means inside of the system. So exogenous errors means that on average, our errors are equal to 0. But what this means in practice is that our errors are not correlated with the predictors in the model. That is, the magnitude of our error does not depend on any model predictor. We'll see what this means in a second, and I'll show you some examples of endogenous errors. But sometimes the extent to which our guess is wrong is correlated with the value of our predictor. Sometimes we might be more wrong for high numbers than we are for low numbers, right? On X. If that's the case, we have endogenous errors. That is, our errors, the value of our errors depends on the location of X. We cannot have that if we want to have good causal inference from a regression model. The reason we can't is because we're going to have bad standard errors if we don't meet this assumption, and our uncertainty estimates will be incorrect. Errors cannot be correlated with predictors. Okay, we have to have linear independence of predictors. That is, we cannot have predictors that are functions of each other. And this is actually really tricky to do in practice. Outside of an experimental setting, right, where we know that assignment to treatment is randomly assigned. But for example, let's think about if I were to study education, years of education, current income in employment, and the state you were born in, right, in the US. So we could think about years of education. Well, maybe not state you were born in. Let's think about parents' income. That's an easier one, okay? So parents' income and your years of education, are those two things related to each other? Absolutely, right? Wealthier parents, parents with higher incomes, have children who tend to have more education, right? When parental incomes are lower, we tend to see children with lower levels of education. And there's all kinds of reasons for that, right? Higher income parents tend to prioritize their children's education to make them competitive in the marketplace, or because they intrinsically value education or whatever, but they'll spend their resources to make sure their children get good educations, right? This is common. So there's very clear gradients of college attendance by income in the United States, right? Higher income families tend to go to college more frequently. So if I have I write a regression equation where I say income equals beta 0 plus beta 1 education plus beta 2 parents income. Do I have independence of predictors? Absolutely. These two values are correlated with each other. Right, so correlation, education, parent income is not equal to 0. I can state that pretty definitively. Right? In this, so my estimate for beta 1, a valid causal estimate of the effect of education on income? No, it's not. These two predictors are correlated with each other. If I don't have linear independence of my predictors, I do not have a valid causal estimate for beta, either beta 2 or beta 1. Those predictors are correlated with each other. Because of that, I cannot interpret them as causal estimates. Effectively, what we're doing here is we have a system. The reason for this is I can't disentangle the effects. Let's say education. You know, education has a relationship to income, right? But we also know that parents' income is also related to income, right? Because like if your parents in a high-powered position, they can use their social networks to connect you to people that might lead to you getting a better job. But we also know that parents' income is correlated with education, right? So we know that parents will also use their resources to improve their children's education. So we can't determine in this system what is the unique impact of education on income, because we have confounding with parents' income, right? So putting them both in the model does not break these arrows. It just makes it so that we're estimating the joint relationship of these three things happening at the same time, right? This is called a directed acyclic diagram. These are really useful for causal inference, but we're not going to go too far into them now. We can think about drawing out causal diagrams. I think it's a really helpful way to think about these systems, right? By mapping out what are the relationships across our variables. And in this case, for example, we could say that maybe like, just to kind of push this a hair further, could we say that income causes education? Like my income causes education. I might like, if my income goes up, will my education go up? It could. Sometimes people might, as their income goes up, decide to go back to school, right? Or some people might have a very low income, and because of that, decide to go back to school, right? So there are kind of two ways we can see income causing education. What about parents' income? Can a child's income cause a parent's income? I mean, only in the sense of like transfers, right? Maybe we think about like parent income when the child was age 5, right? And hold that fixed, right? So in this case, there's no bidirectional relationship here. Parents' income and education, can a child's education cause a parent's income? Not really. So we do have some directionality here. And we can think about how that affects our interpretation of the results. But we have to be really careful when we think about these things. A lot of times people will just put predictors into a regression model and then interpret them. Oh, well, the effect of education on income is beta 1. But in fact, we don't know that, right? Because the effect of education on income is in part caused by parents' income. And parents' income also has an effect on income, right? So the effect of education on income, which is this right here, isn't isolated. We haven't isolated that. in our system so that we can effectively estimate the causal effect. So in this case, we do not have a causal estimate. It's not to say it's not useful, but it's not a causal estimate. And we have to have constant error variance. That means that the variance of our errors can't be a function of location, right? The spread of the errors from y has to remain constant. So we can't see like a higher absolute error as we go away from 0. We'll show you what that means. It fans out typically. This is called homoscedasticity. It's a funky word, but it basically means constant error variance. You may hear heteroscedasticity. That means non-constant error variance, but I'll show you what this means as we go. These are the 4 assumptions that must be met for a linear regression to be valid and unbiased for its estimates of beta to be interpretable as causal estimates. These are very hard assumptions to meet. I will advise you that you should basically never interpret regression estimates as causal estimates unless you have explicitly designed for causal inference. It is hard to meet these assumptions. So be very careful with interpreting regression parameters as causal. They are not unless you've designed for it. Okay. For predictions to be unbiased and consistent. So here we're talking about beta being unbiased and consistent, right? Meaning that it's not systematically higher or lower, and that as we get more and more data, it'll converge to the truth, right? For y hat to be unbiased and consistent, it's actually quite a bit easier, right? Because now we don't really need beta to be exactly measured. We just need our predictions to be accurate. We need the system to produce accurate data. And here I'm using that notation, y hat equals beta x. I can easily rewrite equals beta x, where I'm combining beta 0, beta 1, and beta 2 in the beta, and education inherently comes into x. And effectively, I'm saying multiply the vectors betas by the matrix of predictors. It's just kind of simplifying the notation a bit, but if you see beta x, that just means all the betas and all the x's are in a linear relationship with each other. Now, if I get a more complicated regression equation, that won't work. But this would mean beta 0 plus beta 1 times x1 plus beta 2 times x2 plus yada, 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 beta n times xn. Okay, so for predictions to be unbiased and consistent, which we can just read as accurate and reliable, right? The linear model must approximate the data generating process. So that requirement is still true. The basic relationship between x and y has to be linear. We do have to have constant error variance, but I don't care about independence of predictors anymore. And I also don't care about exogeneity of errors anymore. I can drop those 2 assumptions if all I want to do is prediction. So I do still have to demonstrate that the linear model is appropriate. And I do still have to demonstrate that the error variance doesn't depend on the location of x. But if I have those 2 things, I can still generate accurate predictions. So the threshold for accurate prediction is lower than the threshold for causal inference. So even if we don't meet all those assumptions for causal inference, we can still use regression models to make valid predictions. Okay. I've already said this, but when we don't have the exogeneity assumption, meaning there's unmeasured confounding, meaning there's some variable that we have not measured that affects y in a way that our regression doesn't model, right? When we have unmeasured confounding, which randomization takes care of that problem, right? Or we haven't met the linear independence assumption, we can't interpret beta as causal. When we can't meet the assumption of linear model or constant error variance, we can't make valid predictions. So as you're critiquing a regression model, as you're reading a paper and thinking about a regression model, you want to think about these. You want to think about, is the linear model appropriate for the relationship between these 2 measures? Do we think it's a line? right? Or do we think it's something else? Do we think there's some other variable that's not in the model that impacts the outcome? If we don't have randomization. If we have randomization, that'll be balanced across the two treatment and control groups, right? But if we don't have that, are we sure that the treatment and control groups are actually the same? Or are they different in some way that we haven't measured, right? Okay. Here's a couple ways to write a linear regression model. We've seen this before, but this is maybe new. So we're going to say that yi is equal to beta 0 plus beta 1x plus beta 2x2 plus epsilon, right? And we can add any number of betas and x's we like, and this model still works. And then we can say that the error term follows a normal distribution with mean 0 sigma squared. The randomness in our regression model comes from the errors. The errors follow an approximately normal distribution centered around the line beta 0 plus beta 1x plus beta 2x. So on average, if we were to take lots and lots of draws, for lots and lots of predictions, those errors would follow exactly normal distributions around the regression line. Another way to write it, though, is we can actually kind of fold the error term into the regression equation, and we can just say that y is distributed normally around the line with average equal to beta x and variance sigma squared. So you may see either of these. The subtle differences, it's okay if they don't make sense. Effectively, what we're doing here is we're substituting, we're kind of rewriting, we're writing epsilon out, right? And we're going to say this itself is normally distributed, and that's where our noise comes in. That's where our error comes in. Right? The normal distribution is what produces our error or our randomness in the process. And so we can write it either of these ways. Both are accurate. If we're saying y is distributed normally, we're saying it's distributed normally around the regression line. Right? That is, mu is usually our first parameter in a normal distribution. Here, our mu is variable. Our mu depends on the values of x and beta. It's a little funky, but these are just the two kinds of notations you may see. And again, this tilde means distributed, right? So let's work through some examples. That's kind of our theory lecture for the day. Let's go back to our criminal record data. And you've already done this, but we're going to kind of take it a step further and think about the standard error. So I'm just going to do some simple data cleaning to make this look a little better, but we're going to take our criminal record data again. I'm going to turn race into a white-black variable because I think that's easier to read than 0, 1. And I'm going to make crim-rec a logical, that is true-false criminal record. And I'll take those three variables, right? Because those are the three that I'm analyzing. So this is what that data is going to look like after I clean it and make it look the way I want it to look. I'll have callback equals 1 or 0, race equals white or black, crim-rec equals true or false. No reason I couldn't make callback true or false as well. I just didn't do it here. Okay, so we know how to compute the sample average treatment effect, right? We're going to filter for crim-rec is true, group by race, and then compute x bar as the sum of callbacks over n, or that could just be the mean of callbacks, it's the same thing. The standard error, right, is going to be the standard deviation of callbacks divided by the square root of it. Right, remember last time we saw standard error sampling distribution for a statistic x bar, right? So the SE x bar is equal to SD x over square root of x. Yeah, that's all we have here. Our control group will compute the same way, and then we can compute the sample average treatment effect as x bar minus the control mean. And then to compute these standard error of the sample average treatment effect. To add sum of errors, to add standard errors, you could say like the sum of SE, rather, SE1 plus SE2 general is equal to the square root of SE1 squared plus SE2 squared. Right, this is the general rule for adding variances, and a standard error is a form of a variance. So we just sum up the squares and then we take the square root of it. Because the sample average treatment effect, right? The variance in the sample average treatment effect depends on the variance in the control and in the treatment, right? It depends on both of those standard errors. So we have to account for both of those. So we end up here with our estimated treatment effect for criminal records for black testers and white testers. Here's the standard error for both of those treatment effects. And then here's the sample average treatment effect of the criminal record on white testers is minus 0.73, right? And the standard error of that treatment effect is 0.0494. Okay. So this is X bar for the treatment group, not the control group. The sample average treatment effect for black testers is minus 9 points for a criminal record with a standard error of 0.03. Yeah.
So if we relate this to regression,
That's where we're going. Exactly where we're going next. So that's just computing it by hand, right? We just computed the whole thing by hand. It's basically what you did in like homework 2, but then we added the standard error computation, right? Now, we can do the exact same thing using regression as you did in, was that homework 7? I don't remember. One of them, you did this with regression, right? So the linear model, so let's kind of walk through. We are interested in causal estimates, right? In this research design, we want to know the causal effect of a criminal record on callback rates. We really want to understand that. We also want to understand the causal effect of race on callback rates. And we want to understand jointly how race interacts with criminal records to affect callback rates. So we have kind of 3 sets of causal estimates that we're interested in. Okay, so first, does the linear model approximate the data generating process? That is, how would we talk about a linear model? Let's kind of first write out what our hypothetical linear model will look like for this question. So we'll say callback is our outcome, right? Callback I equals, what comes first? Is 0. That's right. Plus beta 1 times code race plus beta 2 friend rec sub I plus beta 3 race sub I times friend rec. Right? So our ultimate model is going to have 3 betas, beta 0, beta, or 4 betas, beta 0, beta 1, beta 2, beta 3. Okay? Now, do we think that a line is a good representation of the relationship between these variables? What scale is callback on? What scale is race on? Okay. What scale is criminal record on? So we have a lot of binary variables. So do we think a linear model what would it mean for a linear model to approximate the data generated process? It would mean that race, we would effectively be doing kind of what we're doing in the regression model, where we're saying that, well, when you are black, you get we're effectively asking for y hat. What scale is y hat going to be on? Our outcome is 0, 1. So our actual predictions will be 0 or 1, but the scale of y hat, our expected value of y, is actually going to be a probability. And that's going to fall on the 0, 1 interval. So it's going to be a real number between 0 and 1. Can't have probability less than 0, can't have probability more than 1. Right, so our expected value will be a probability. Right, the outcome is always 0 or 1, but our regression model is going to tell us what's the probability that it's a 0 or 1. So typically, we might think of this as, let's just kind of pretend 0 equals 0.2. Let's say theta 1 equals 0.1. Theta 2 equals 0.3. So kind of ignore the interaction. So we can end up with a model under this hypothetical where everyone starts with the 0.2. We'll say the tester is black, and that this coefficient applies to black testers, not white testers. We'll call it 0.1. We'll say data 2 is the criminal record, and that's when the criminal record is true. This is not actually how it works, but we would end up with a 0.2 plus 0.1 plus 0.3. We would end up with a 0.6. We would say in this case, we predict with a 60% chance that the respondent will get, the tester will get a callback. Right, but what we're assuming is that the effective race just adds up with the effect of the criminal record in a linear fashion, right? They just simply add together, right? We don't have any kind of nonlinearities in the system. We don't have any kind of exponential processes in the system, right? Linearity is actually really tricky to think about with binary variables. It's usually not a great fit because a line can produce predictions that go below 0 and above 1, right? A line, even if, right, our kind of range of true values can't go outside here, there's nothing stopping a line from going above 1 and below 0, right? In this case, it won't because we have categorical predictors. But if we had continuous predictors, it easily could predict probabilities higher than 1, probabilities less than 0. Don't worry too much about this, but that's what it means to think about the linear model. Exogeneity, so it's a questionable assumption under a binary outcome, linearity of the data generating process. That is, it's difficult to say. So the other thing is is going from 50 to 75% probability equivalent. So we have kind of differences in step size, right? Like an increase in probability from 50 to 75 might be different than an increase from 95 to 99, even though it's like 25 points, right? You can't move, like a big move at 95%, you actually can't move very far toward 1, right? Whatever. We have a kind of compressed space, and anytime we have a compressed range for data, linearity is going to be questionable. So if it must fall between 0 and 1, the linearity assumption is going to be tricky because numbers can't go below 0 and numbers can't go above 1. So if something already has a probability close to 0 or close to 1, the linear model is not going to work very well. That's roughly what that means. And that's where something like a logistic regression might be more useful. But it's fine. Okay. Exogeneity of errors, meaning is there something outside the system affecting our results? We randomized, so we have that controlled. The treatment and control group are identical based on design, right? Linear independence of predictors, randomization also handles that. We don't have to worry about that. Constant error variance, we can check that after estimation. In this case, it is going to be violated. We are not going to have constant errors, and I'll show you what that means. Now, that does mean our standard errors might be biased a little bit. In this case, it's a trade-off we'll be willing to accept. Okay, so to estimate standard errors of beta, right? This is where things get funky. So we know that the sample mean has a sampling distribution, meaning anytime I sample the height of 10 students from among Rutgers students, if I take a simple random sample, I could get a lot of different values for that sample, right? I get a lot of different values for the average of those 10 heights. Let's say that heights follow a normal distribution, and let's say what the average height, let's say it's 5'6", and that's 65 inches, sure. And we'll say, well, we're going to draw 10 heights with a mean equal to 65 and a standard deviation. Let's say the standard deviation is 7. So in this case, here are 10 random heights from Rutgers, right? These are 10 students. And then let's compute X bar is the mean of heights. Let's run this code a few times. Show X bar, 67.3, 62.1, 65.0, 67.6, 65.3, right? 5.3. Anytime we resample, we can get a different average. We're good with that, right? So anytime I draw a new sample, I can get a new average. Now, let's say what the shape of this is going to look like. Let's run this 10,000 times. And we'll say output bracket I equal to X bar. So I'm using lists I can index using the double bracket notation, and I don't have to initiate them as a particular size, which is nice. So I can just make it an object that's going to take every single X bar I compute and put it in a list. So now I have 10,000 means, right? I'm going to do rbinds to reduce it to a data frame. And then let's look at a histogram of it. Anyone want to guess what shape that histogram is going to look like? What does the central limit theorem tell us this is going to look like? It will look normal. Sorry, these binders. Come on. Okay, there we are. There's our 10,000 means, right? Hey, it looks like a normal. This happens under random resampling, right? If we draw a random sample of students and we repeat that exercise many times, the distribution of the mean of the means of those sample means will be approximately normal, right? So here we have a mean of 65, which will be, again, according to the law of large numbers, the sample mean will converge, right? X bar will converge to mu. So the most frequent value we get here is 65. We get a sampling distribution that has 95% interval that goes between about 60 and 70, right? Meaning our standard deviation is about 5 for our sampling distribution, which is lower generally than the sampling distribution for X. So the sampling distribution for X had a mean of 65 and a standard deviation of 7, right? But if we were to take the SD of output, we'd get 2.2, right? So we actually have a far lower standard deviation for X bar than we do for X itself. We're more certain about the location of the average height than we are about any individual's height. And that should make sense, right? If I were to pull one individual, they could be very tall, they could be very short, they could be right in the middle. But the average, we should be more certain about. Okay, this is the central limit theorem and the law of large numbers in practice, right? As we draw lots of samples and we compute their means, the distribution of those means is normal. And so what we can do is we can think about any sample of 10 students then, X bar is drawn from this distribution. X bar is actually sampled from this, right? So we can describe the location of X bar as coming from a random distribution that has mean 65, standard deviation 2.2. That's a lot, but that's what a sampling distribution is. We're saying that the statistic X bar, which represents the population average mu, itself has uncertainty. X bar has uncertainty. Anytime we draw a sample, X bar could be one of many values. It follows this normal distribution. We can estimate that normal distribution. We can estimate approximately what that normal distribution looks like from our data. So let's do that. We can treat the standard error of beta as the standard deviation of its sampling distribution. That is, we can say that a beta comes from a distribution like this. Our betas in our regression equation come from sampling distributions. We are uncertain in any one sample about the true value of beta, but we know that it comes from some distribution of possible values of beta we could observe, right? We observed one of them. We didn't observe a ton of them, we observed one, but using that one, we can approximate the shape of this curve. That's kind of cool. So if we assume that those errors are normally distributed, we can treat the standard error of beta as the standard deviation of the sampling distribution. So we can say that beta itself is normally distributed, where the mean for beta will be equal to beta hat. That is whatever we observe in the data. And the standard error will be estimated from the data. So the standard error beta is a complex calculation, just the sum of the squared residuals divided by the sum of the average of it's the squared residual minus the square of the differences. It's a little funky, but or rather, I'm sorry, it's the average residual over the sum of squared residuals. But you don't have to compute it yourself, R will do it for you. So we're going to define the sampling distribution for beta this way. We can construct confidence intervals for beta using our actual estimate of beta and then plus or minus whatever critical value for alpha we choose, if that's going to be a 0.05 for a 95% confidence level, or a 0.01 for a 99% confidence interval, right? We can just do exactly what we did last week to compute confidence intervals for beta rather than for X bar. And then we can conduct a z-test or a t-test exactly as we did last week. So we can treat beta like any other mean, right? It is like any other mean. We can treat it exactly the same as we treat it like X bar, and we can construct confidence intervals, and we can conduct t-tests. These are what statistical significance tests are when we look at them in scientific papers. is they're just t-tests of a mean. So here's what that model for race and criminal record looks like. We estimated this before, right? You did this in your homework. This is all you need to estimate that model, because R, when it has an interaction, will automatically put in the additive terms in addition to the interaction. It'll do that for us. So callback is a function of race times criminal record. So implicitly we'll get, R will give us this model. We tell R to do this. It'll give beta 0 plus beta 1 times race plus beta 2 times criminal record plus beta 3 times race and criminal record. And we can see that. We get an intercept. We get beta 1, beta 2, and beta 3. Yeah? Now, here's where things get new. We didn't really look at this side of things last time. We just looked at this. These are beta hat. The estimate column is beta hat. That's our point estimate for beta. One value of beta that could have been observed among many possible values of beta. That's the one we got when we ran this study. We could have gotten different values though. How different could those values have been? Well, we don't know exactly, but based on the variance we saw, we think that there's a standard error for this beta of 0.025. Is that highly variable or relatively certain? 0.025 on an estimate of 0.14. It's pretty stable, right? So how far away do we need to go to get a 95% confidence interval? 1.96 is Z. So we need to go about 2 times the standard error away from the estimate to get an interval. So in this case, our rough 95% interval, again, just back of the envelope, kind of do it in my head, but it's 0.14 plus or minus 0.05 is a 95% confidence interval for beta 0. 2 times the standard error. The estimate plus or minus 2 times the standard error. That's pretty crudely a 95% confidence interval. So in this case, 0.14 plus or minus 0.05. So we could say that a 95% estimate, a 95% interval for the intercept is 0.09 to 0.19. Maybe that's wide. I don't know. That's a qualitative judgment, right? But we can say a 95% interval is about 0.09 to about 0.19. Okay. Race white, 0.199. Standard error of 0.038. Criminal record, negative 0.9, 0.09. Standard error of 0.035. Then our interaction term similarly. Let's move to these t-values. So it conducts t-tests on each of these. What is the null hypothesis in this case? So our null hypothesis, for example, on the homework was mu Obama minus mu Kane equals 0. What do you think our null hypothesis is going to be here? Implicitly, for each of this, our null hypothesis, beta 0 equals 0, 1 equals 0, 2 equals 0, and 3. Those are our null hypotheses. Our alternative hypotheses are beta 1, our alternative hypotheses are that these values are not equal to 0. So our null hypothesis is that there is no relationship between race and callback. That for an increase in race, a difference in race, we should see no change in callback. For a difference in criminal record under the null hypothesis, we should see no change in callback. So what are we going to do here? Implicitly, we're going to take H0 to be true. Let's take that in the case of beta 1. What's the value for beta 1 hat that we've estimated? Or I'm sorry, what's the standard error for beta 1 that we've estimated? 0.38. Okay, so what we're going to do is we're going to assume instead of 0.199, we're going to assume that this is 0. That's what our null hypothesis test is going to do. So it's going to center the sampling distribution for beta hats on 0. And it's going to have a standard deviation of 0.038, which means roughly that 95% of the mass will fall between negative 0.76, positive 0.76, right? 2 times the standard error. We'll draw that as our hypothetical sampling distribution for beta 1. Now, what did we actually observe? 0.199. How likely are we to observe 0.199 from this sampling distribution? What would be the probability of drawing 0.199 if this were the true sampling distribution for beta 1? It'd be real close to 0. There's very little tail, there's very little mass of this normal at 0.199, right? Under this distribution, we've got a high chance of drawing something between -0.076, right? We have a high chance of drawing something in this range. A very low chance of drawing something this extreme. So what we're going to do is we're going to say, okay, we're actually going to estimate our chance of drawing something like 0.199 if the sampling distribution for beta 1 were centered at 0 is 0.000003. We can measure that as a t-value. So we can say t equals roughly 0.199 divided by 0.038 equals, what does it say, 5.6 or something? T is the number of standard deviations away from 0 that our estimate is. How many standard deviations away is it from 0? So once we know the t-value, we actually don't even really need to check this, because we know that something on a normal distribution is very unlikely to be 5 standard deviations away from the mean. Right? We know that. If the mean is 0, this is how far away it would be. But we can go ahead and run that test using the p-norm function, p-norm on this t-value, with a normal 0, with a standard deviation of 1, because we've converted to a t score now, or rather than, or a z score now, has this probability of being drawn, virtually 0. So when we're doing a significance test, we're saying, imagine this were true. Imagine beta 1 equals 0. Imagine that the average of beta 1 equals 0, but then any time we draw, we have some variability, and we want to be 95%. We want to do this test at a 95% confidence level, right? So we're going to go 2 standard deviations away from the mean. And we're going to say, if our value falls inside this range, then we can't reject this. If our value of beta 1 was not 0.199, but was 0.03 minus 0.03, it would fall like right here. And that falls firmly in a range of likely values from that sampling distribution. So we can't reject that beta 1 is 0 if we observe this. Now, if we observe this, we can be highly certain that the sampling distribution for beta 1 does not center on 0. Not to say we know where it centers, but we have not said it centers on 0.199. All we've said is that this is not correct. That's what our test does. Is this correct? Yes or no? This test says no. So let's repeat that for the interaction term. Beta 3 equals 0. So another normal. Again, every null hypothesis test will be centered at 0. That's what it does by definition. What's our standard error here for beta 3? We'll just round it to 0.05. So we'll go out to what's going to be our 95% interval range, roughly, if we're using the rule of thumb that we can use 2 standard errors. Minus 0.1 and positive 0.1, right? So we can draw a normal that has a 95% interval approximately in that range. What did we estimate for beta 3 hat? Minus 0.08. Where's that going to fall? Could we have observed beta 3 if the null hypothesis were true for the sampling distribution? Definitely, right? That is firmly within this confidence region. So in this case, we can go through and read off our probability. There's a 12% chance, a 13% chance of drawing something like a minus 0.08. Now, if we're using a 95% level, we cannot reject the null hypothesis, right? That's too high a probability. We don't know that the sampling distribution for beta 3 is not centered on 0. We have not learned that. When we do significance tests, we're never accepting the alternative hypothesis. We're never accepting beta 2 equals 0.199. We don't know that. What we know is that the sampling distribution is not 0. And so effectively, go back to first example again. Right, here's our null hypothesis test. Here's our result. We can guess that one possible sampling distribution could look like this, just shifted this way. And we're going to estimate a confidence interval around beta for that. However, what's the problem here? If we were to repeat this experiment, are we going to get the same value for beta 1? No, we won't. It will be different. It may not be different by very much, but the next experiment could draw beta 1 that's here. The following one could draw beta 1 here. The following one could draw beta 1 here. Or here. Right? Each of these results in different hypothetical sampling distributions. If we center that distribution there, we don't know the true value of beta 1. We don't know exactly where it's centered, but we can test, is it centered at 0 if we observe what we actually observed? And we rely on the variance of the data to assume that the variance of the real distribution will look similar to what we observed in the data. That's what a null hypothesis test does in the context of regression. It's a weird thing to do, but does it make a little sense in terms of the logic of it? Could it have come from this distribution? That's the ultimate question we're after. Let's take 5. And I know if you need to take off this one. Yeah.
So this makes a lot of sense, and it's cool to see it illustrated like this. Because I've read last semester and I included this in the homework. exactly what you said, that they assume that the null hypothesis is true and look for like if these values would be outside of the range expected by the hypotheses.
So let's use our OLS model then to make predictions. We've already seen how we can do this using just the equation, right? We know that we can just solve for y hat using beta 0 and beta 1 and some value of x. But sometimes it's really helpful to do this more systematically, right? And maybe we want to make predictions for things that we didn't observe in the data, right? Maybe we want to make predictions for hypotheticals. In this case, I'd like to make a prediction for every possible value that could occur in the data for race and criminal record. One really easy way to do that with the tidyverse function is the complete function. So I'm going to make a data frame that has the values black and white and true and false. Those are the values that could occur. Then I'm going to use the complete function to make all possible combinations of race and criminal record. We'll get black, false, black, true, white, false, white, true. Those are all possible combinations, right? Now what I'm going to do, I'm calling this preddat. This is going to be the data that I predict over. I want my regression model then to make a y hat for each of these rows. I want to know what the expected probability of a callback is for each of these groups. So what I can do is I can use the predict function in R. Now we could just compute this ourselves, but predict, once we get sufficiently complicated regression models, predict will make our lives a lot easier. Or if we have a lot of data we want to predict over. So predict takes a couple arguments. It takes a model first. So in this case, we called that CROLS, right? CROLS. So we're going to give it CROLS as our model. We created our prediction data frame with all possible values of our data, right? This is our prediction data frame, preddat, 4 rows. And we're going to call that argument new data. And we want to get a confidence interval from this. The other argument you can give this is prediction, which will not only sample, or it won't sample X bar at that point, or Y bar, it will sample Y itself. And remember when we looked at the height data, remember height was more variable than the average of height. This is going to give us an interval for the average of callback, not for any individual callback, right? Because that will always have more variability than the average. A prediction interval will always have more variability than a confidence interval. That is, predicting Y inherently has more uncertainty than predicting Y bar, right? Okay, so I'm going to put this all in a data frame just to make it convenient. But this is what that predict will give me. It'll give me a fit value. That is the expected average callback rate for each row of my preddat, a lower bound for that confidence interval, a 95% by default, and an upper bound for that confidence interval, a 95% again. So we get Y hats, lower bound, upper bound. And I'm going to just kind of stick it all together with a mutate to put it in a single data frame along with my prediction data. So now I'm going to have black, false, black, true, white, false, white, true. Here is the expected callback rate. Here is the confidence interval. Right, so my black expected callback rate is 0.14. My white expected callback rate with no criminal record is 0.34. And here's the interval for those expected callback rates. Yeah.
What interval is this?
0.95. That's by default for predict when you say confidence interval. You can assume anytime you see a confidence interval, generally it's a 95%. That's the standard. There are reasons to use other confidence interval sizes, and that's an arbitrary, 95% is arbitrary. There's nothing magic about 95%. It's just a norm. It's just the norm for reporting intervals. Sometimes though, you'll see others. Some people like to be cheeky and make like 89% confidence intervals or 91% confidence intervals just to remind you that 95 isn't magic. But It's not a big deal. Okay. So we're clear on what this is, right? This is our data, and these are our predictions. Okay? These are not observed, these are hypothetical data, right? We didn't use the observed data to do this, but of course we would see these cases in the observed data, right? And it would predict the same for every single Black false criminal record testing, right? Okay, so here is our parameter estimates for treatment and control, right? Just to kind of remind us what we saw there. So when we computed the means and the standard errors manually, right? Black 0.058, Black 0.058, standard error 0.0157, which would generate a confidence interval about like this, right? So we can see, right, that these line up, these predictions and our means line up exactly, right? So our expected values of a regression will always be equal to the observed means from the data for those cases, right? To the extent that we've observed those cases, the expected values from the regression should always be equal to those computed means. So X bar in this case is equal to Y hat. Kind of weird. Okay. Visualizing a confidence interval could look something like this. I'm going to use geom crossbar to show you the range of the confidence interval for white testers with a criminal record and without a criminal record. These are Y is our expected callback rate, right? And we can see in general, right, the false groups, we see a clear difference across Black and white. And the true groups, we see a pretty clear difference across Black and white. So this is a good way to visualize those regression predictions through a confidence interval. And it doesn't take much once I have my upper and lower bounds and my point estimates, right? In this case, the crossbar argument will take a Y for the center line, an aesthetic Y for the center line, an aesthetic Y min for the lower bound, an aesthetic Y max for the upper bound. Make this box. I'm saying use criminal record as a fill to color it in. And because it's binary, it'll know the default colors to go with in ggplot for a binary are pink and blue. But we can change those colors if we like. That's, you know, optional. Alpha is just going to make them transparent so we can see if there are zones of overlap. Alpha ranges from 0 to 1. 1 is totally opaque, meaning you can't see through it. 0 is totally transparent, meaning you can't see anything. I find that 0.5, 0.7, those are typically good alpha levels to use if we want something to be transparent. So this is a nice plot, right? I think this is actually more fun to look at generally than this. So when in my papers, I tend not to show this. I tend to show something like this. It's the exact same results. It's just presented in a different way. I'm using predictions to get things on the scale of the outcome, because what we're really interested in is expected callback rates, right? That's what we're after. I'm not necessarily interested in beta 1 itself. I'm interested in how it affects callbacks. And this shows us. Okay, so to use OLS to obtain causal estimates, the easiest way to do it is with the randomized control trial, an RCT, right? That is the gold standard for using OLS to obtain causal estimates. We saw earlier that we could use something like a difference in difference design. Remember the minimum wage experiment? If we can meet, there's just stricter assumptions that we have to meet if we're going to use non-randomized methods, right? If we're going to use a matching-based method like a difference in difference, those are called natural experiments. We have to make additional assumptions in those cases, but we can do it. And those are also cases where we can use OLS to obtain a causal estimate. The key being here that we have designs to have either very closely matched pairs or full randomization, right? We've designed so that there are minimal differences across groups or no differences across groups. That's the key, no differences across groups. You can always use instrumental variables. That's something that Professor Apel may talk about. I know he talks about it in his advanced causal inference course. He said he was going to send everyone an email as well. I don't know if he's done that yet to introduce the class for next semester. So look out for that. And regression discontinuity is another example. But there's so there's a lot of kind of tricks people can use to get a causal design around OLS. RCTs, randomized controlled trials, is the most straightforward and most common way to do so. But in the social sciences, you will see natural experiments, instrumental variables, regression discontinuity designs used a lot. Regression discontinuity kind of uses arbitrary breaks in the data to think about outcomes. So for example, if a school has an SAT requirement for college admission, like 1,400 to get into a college, we could take two students, one at 1,399 and one at 1,401, who are basically identical, right? They're only 2 points away on the test score. The only reason they're different is that that kid with the 1,401 is going to get into the good college. And we can use that discontinuity. There's a clean break right there. We can use that to estimate the effect of that college on later outcomes, assuming those two students are identical, right? Assuming that 2-point test difference is not meaningful. That's what a discontinuity design does, is it takes these arbitrary breaks as places where we could say the two people on either side of this line are actually identical, and then look at what happens to them because they were exposed to different things just because of that line, right? But it's not too important for us today. Let's talk about OLS for prediction and description though. And I'll be honest, this is 98% of how I use regression for my work. I do primarily descriptive work. That is, I'm not usually interested in causal estimates. I'm usually interested in understanding relationships across systems of variables and to think about group means, right? To think about how groups look on average, or to think about helping us understand uncertainty in a context where our data, where we might have relatively weak data, right? But let's kind of work through one example here. I've put, if you want to follow along, that's cool. If you don't, that's fine too. I put some data on police expenditures on our GitHub page that you can download if you like. And this is what's in that budget data. These come from a variety of federal data sources. Sorry, my allergies are going nuts today. We have a FIPS code. Has anyone seen these FIPS codes before? These are 5-digit identifiers for counties in the United States. So 1001 is actually 01001, but that the first 2 digits identify the state, Alabama, and the third 3 digits identify the county in the state. So every single county in the United States has a unique 5-digit identifier. And a lot of times in geographic kind of analysis, we're going to use counties as an identifier. And in the case of criminal justice, that makes sense because those are also jurisdictional boundaries routinely. That is, like, a sheriff in one county has jurisdiction in that county versus another. That is, a criminal justice system is often administered. Some pieces of the criminal justice system, like jails, are administered at the county level. Anyway, what we're going to do here is we're going to take the county, and that's just a categorical identifier. We could think of it like an ID code. EXP Police PC is dollars spent on policing in that county per person, per resident. PC stands for per capita. So this is police spending per resident in that county. So in this county, they spend $169 per person on police in a given year. Officers, PC, this is, I think, scaled to per 1,000. So this is how many officers are there per 1,000 residents. 83.3 in this county, 32.1 in this county. This gives us a measure of officers per person. How many officers are there relative to the population size? Revenue property tax per capita shows us how much property tax revenue does that county collect per person in the county, which just gives us a sense of how strong are the county budgets, how much money do they have to spend overall. Places with higher property tax revenues per capita have more money to spend, have wealthier residents, have higher property values. Property tax is the primary way that local governments fund themselves in the United States. So high property tax means local governments tend to have more money to spend. Violent crime is just a binary for whether the violent crime rates in that county, according to the Uniform Crime Reports, are higher or lower than the average. Segregation, BW high, is whether black-white segregation in that county, residential segregation is higher or lower than the average in the country. And same LW is whether segregation between Latinx and white people is higher or lower than the average in the country. So we have two measures of racial and ethnic segregation, one measure of violent crime, one measure of overall revenues, one measure of police staffing, one measure of police spending, and a county level identifier. It's a 500 row data set. So we have 500 counties in here. Cool. This was actual working data. I was building a paper around. I haven't published on this, but this was, if you download this data and want to work with it, let me know, because there are papers to write with this for sure. Okay. So here's our data. Let's model spending on police per capita. I want to know, what are the characteristics of counties in the United States that spend a lot of money on police, right? That's my question. My question is, who spends a lot of money on police? And I think that police spending is going to be a function of three variables. I think it's going to be a function of property taxes first. That is, you got to have money to spend money, right? So those counties with larger budgets should be able to spend more on police generally. Those counties with higher crime probably want to spend more money on police as well. And those counties with high levels of segregation also probably want to spend more on police historically because of the relationship between racism and policing in the United States. And also that segregation is a partial cause of crime too, right? So we have lots of reasons to put segregation in the model. So I think that spending on police is a joint function of these three measures. So using an OLS model to describe that, I'm going to say that police spending is normally distributed following a linear relationship described by beta x with a variance sigma squared. And I'm going to propose an initial model that looks like this. My initial model is beta x is going to be equal to beta 0 plus beta 1 taxes I plus beta 2 crime I plus beta 3 segregation I. That's my initial model. What two assumptions do I need to meet for my predictions to be valid? Pop quiz. Linear, functional linear form. So this equation needs to describe the relationship between y and these three predictors. It needs to be linear in form. It's not going to be. That's okay. We can fix it. What else? We need our errors to be constant. Our error terms have constant variance. It's also not going to be true here. And I'll show you that. Okay. But here's how we would estimate the model. Call it budget FIM1. Police spending per capita. It's a function of property tax revenue plus violent crime plus segregation. Okay. So tidy just gives me a nicer output. Tidy is a function you can use to give clean output of some kind of objects that are otherwise messy, like the regression output usually looks like this. That's a lot. Well, maybe all I want is this table. Often all I want is this table. I don't want this or this. So if all I want is that table, I can use the tidy function to give me just that table of estimates, of parameter estimates, right? So it'll give me my betas, my standard errors, my z statistic, and my p-value. A lot of times that's all I want. Okay, so what do we see here? When property taxes are 0, violent crime is low, segregation is low, we expect a county to spend $116 per person on law enforcement. That doesn't actually exist. There are no counties with 0 property tax revenue, but that's what the intercept means, right? Sometimes the intercept doesn't actually have any real meaning. It's just a mathematical artifact because we need it to make the line work, right? We're saying for every $1 increase in property taxes, we expect to see a 17-cent increase in police spending per capita. We're saying when violent crime is true, We expect those jurisdictions, when violent crime is high, we expect to see about $6.60 more spending on police per person. And when segregation is high, we expect to see about $6.80 spent more on police per person. Or no, overall. Yes, per person is our outcome. Sorry. Okay, so those are pretty easy to interpret, right? Those betas. Everyone clear on how we interpret those? Feeling okay about that? Questions about interpreting any of these? So my next step, you could just walk away here and say, well, that's significant, that's not significant, that's not significant. I'm done. But that's a crappy approach. We need to check this, right? And how are we going to check it? Well, the first thing we're going to do is we're going to plot it out with our regression line. Is police spending a linear function of property taxes? What do we think? This line is pulled up a lot by this single point, right? We have one extreme value pulling things way up because we've got somewhere that has like $13,000 per capita in property taxes and spends $4,000 per person on police. I don't know, maybe that's Beverly Hills or something, somewhere very affluent, right? But probably somewhere very small and very rich. But anyway, the linear relationship doesn't appear to work well, right? We have all this clumping over here, and it looks like this line is pulled up, it's biased upward by that outlier. And I also don't think we have constant error variance. You'll notice that the spread of dots around the line is kind of clumped in, close to zero, right? This spread looks pretty constant through here, but then as we get further away, the dots start to spread further away from the line. As these dots fan out away from the line, if we were to imagine drawing lines around the range of these dots, that's our constant error variance check. Are they similarly spaced away from the regression line for all values of X? If they're not, we have heteroscedasticity or non-constant error variance. In this case, we definitely have non-constant error variance. And the linear model is questionable. Always look at your data, right? Always look at your data. So in this case, there's nothing that's going to tell us here that the model's wrong. Nothing will tell us that the model's wrong. We just have to look at it. Okay, so, but this is what the data actually look like. And in this case, I can see some problems. The first problem I see is that all these points are clumped together and we have one point that's very far away. We have an outlier. So it looks like we might want to transform these measures somehow. Here's another way to check the constant error variance. You can plot a regression model. So if you just use the plot argument on a regression model, it'll give you a series of plots. One of them is a constant error variance plot. Epsilon is error term. So it'll tell us what is the error term relative to property taxes. And you can see that there's a trend here, right? The errors are becoming more negative as property taxes increase over here. And then this is just the outlier. But this is not what we want to see, is what we see about here. That's almost always what we want to see, is a cloud that has about as many points above the line as below the line, because we want the mean of epsilon to be what? We want it to be 0. Is the mean of epsilon 0 in this range? Definitely not. We have problems here, right? This is not constant error variance. This plot tells us that we have problems with the structure of our errors right now. So let's revise it. Let's critique. We've critiqued the model. We've looked at the distribution of residuals. We've looked at the distribution of X and Y relative to the regression line, and it doesn't look good. Everyone sees why these don't look good when we look at these plots. You could look at this and say that's not a good fit. Can you look at this and say that's not a good fit? Yeah, okay, cool. Bad fit. Okay. I don't think this is a linear relationship. I think there's probably a logarithmic relationship here, because money, we have a lot of inequality in the United States. We have a lot of poor counties and a handful of very wealthy ones. So I think that there's probably some non-linear relationship going on, because police spending can only go up so much, right? It could be really low, and then maybe for those really low to like average levels, we could see a lot of growth as incomes go up. But then once we get like I'm just kind of thinking theoretically here. What I'm assuming with a logarithmic relationship, if we say that spending equals data log taxes is a relationship something like this. So we're going to say that spending would start off really low and go up a lot for small increases in property tax. But then once you get to a certain point, it's going to level off. Because those affluent counties aren't just going to keep spending more and more on police if they don't need it. We're going to say that there's some threshold where you have a good enough police department and then you stop spending, right? So we expect this kind of curve relationship where we get like a diminishing increase in police spending for high values of property tax revenue. And that's a logarithmic curve. That's what a logarithm looks like. It's an inverse exponential curve, right? That is, the rate of increase goes down for higher values. The rate of increase is very large for low values. So often when we have a lot of clumping in our variables, a logarithmic relationship can help us see the differences within them. And a logarithmic process might be modeling things really well, where there's high growth in one portion of the curve and low growth in another portion of the curve. So let's apply a logarithm. I'm going to apply a logarithm to both outcomes here, or to both variables. But once we have it on a logarithmic curve, and then I add in the best fit regression line, does this look better than it looked a moment ago? Dramatically, right? This fit is much, much closer. I don't see super clear patterns in terms of clustering in the data other than near the mean, which is good, right? And in terms of the spread of the variables, I'm not seeing a big difference as we go across the model, right? The spread of the data points relative to the curve looks pretty consistent. So I don't think there's non-constant error variance anymore. And now I think that the linear relationship actually does describe, well, the relationship between the logarithm of property tax revenue and the logarithm of police spending per capita. We call this a log linear relationship, right? So once we've transformed the variables onto the logarithmic scale, we do see a linear relationship. And that's fine. Right now we've met the assumptions on the log scale, and that's okay. If we can transform the variables in some way and then estimate the model and it's functionally linear on a different scale, that's perfectly fine, right? We can work with regression in that way. So I'm convinced that this is a good model now. Here's what the log transformations of the outcomes look like, right? So we went from, this was our initial distribution of police spending per capita. Once we log transformed it, it's a funky thing, but it becomes approximately normal. Once we log transform skewed variables, the distribution of the logarithm is approximately normal. It's a weird feature of logarithms. But we take this skewed distribution and center it out. Property tax revenue similarly, skewed distribution, the logarithm is approximately normal. So it's a nice way to rescale things. So let's fit this on the logarithmic scale. I'm going to take the logarithm of both police spending and property tax revenues because they both have large outliers and are clumped towards zero. And we get slightly different results here. Our segregation measure is now statistically significant when it wasn't before, right? Our crime measure is not, interestingly, but I wouldn't put too much stock in that, right? Because these are predictive models. So do we think that, for example, property tax revenue is correlated with violent crime? Yes or no? Is how wealthy a place is related to its crime rate? Absolutely, right? Wealthy places tend to have lower crime rates. So violent crime is in part explained by property tax revenue. We can't say that violent crime is not related to police spending based on these findings, because violent crime could be impacting police spending through property taxes or through segregation, right? our model has not isolated that. So we can't actually conclude that violent crime is not related to property tax or to police spending from these results. What we've done is we've built a model that can take the values of each of these predictors and generate valid predictions for police spending. That's all we're doing here. We're not interested in interpreting any of these parameters independently. We want to interpret them jointly in a predictive model. And what that means, well, first let's look at our error variance check. Do we see constant error variance here? Remember, this is what we don't want to see, a clear trend in it. What we do want to see when we evaluate a residual plot is this. We want to see about as many values above 0 as below, and we want to see that there's no clear trend in the values of epsilon based on values of x, right? So the variance of epsilon conditional on x is equal to the variance of epsilon, meaning the spread of epsilon does not depend on x at all. That's what we want to see. And we do. Okay, so one way we can interpret this is that for counties in the sample with similar levels of property taxes, controlling for property taxes, similar levels of property taxes, high segregation counties generally spend more on police than do low segregation counties, right? And we can say that we've got an interval between about 0 and 0.14. But high segregation counties, compared to their peers that have similar levels of property taxes. So if we were to take two counties with equally high property tax revenues, one is high segregation, one is low segregation. The high segregation county is typically going to spend a little more on policing than the low segregation county. That's what these findings suggest. About between 0 and 14 cents more per person. That's kind of low relatively, but that's for similar levels of property taxes. Are there any high property tax counties with high segregation? Are there? Yeah, probably. Are there any high property tax levels with, anyway, the segregation is correlated with property taxes, right? So we can't, so saying controlling for property taxes helps us understand comparisons at a particular level, but it doesn't necessarily mean that we would actually ever observe those in reality. Again, be really careful with the causal estimates here. We're talking about average levels, right? Average levels. Okay, so prediction gets more complicated when we have continuous measures than when we have binary measures, but we can still do it just fine. So I want to create a data frame that has possible values for prediction, and I'm going to use a sequence to do that. So I'm going to take the 5th percentile of my observed data for property tax revenue and the 95th percentile of my observed data for property tax revenue. And I want to get 1,000 values between those 2 points. So basically, I'm going to take the observed data, take the 5th cut and the 95th cut. So I'm going to get a 90% coverage of the data, but then I'm going to arbitrarily step it up between the 5th and 95th percentile to just make it even steps between those 2 points. That's what RevTax PC will do. Let's kind of see what that looks like. Data. So this is what that property tax revenue is going to have in it. It's going to start at the 5th percentile, which is 135. It's going to go up to the 95th percentile, which is 1797, and it's going to have even steps between all of those. Then we're going to make our violent crime and segregation. So basically, I'm going to set these up each as independent vectors that take on the range of values that I think I want to model over, that I want to predict over. So I have my violent crime is true, false, segregation, true, false, and then 1,000 values for property taxes. Now I want to make all combinations possible of all of those values. Expand grid is a cool function that if I give it vectors, will combine those vectors to make all possible combinations of those vectors. So in this case, I'm going to create something called new dat using the expand grid function. And you can see that for property tax revenue, we expect to see 4 entries for each one: high violent crime, high segregation, high violent crime, low segregation, low violent crime, high segregation, low violent crime, low segregation. And we'll have those repeated for every single possible value of property taxes. What that's going to let us do is predict over every theoretically possible combination of our variables that could occur. I'm not saying they do occur, but they could. Now, let's use our model to predict. All right, I didn't estimate the model here. We'll just go back to PREDS, right, is going to, just as before, we're going to use predict on budgets M2, which was the model we fit with the logarithms. And because those logarithms are in the model itself, log, in some softwares, you'll have to transform those variables before estimating your model. In R, you do not. If the math is in the formula for the model, you do not have to transform the variable before giving it to the model. R knows to compute logarithms on this. It can do the math inside the model. Stata, for example, will not do that. You'll have to compute log before you estimate the model. But we can then make predictions and then add our y hat lower, y hat upper onto it and produce a plot like this to look at expected police value, expected police spending values. This is under low violent crime and high violent crime, and then low segregation and high segregation. When we look at these curves, we really don't see any difference in the location of the low and high violent crime, right? Those curves really are in about the same place, which is reflected in our models, right? We didn't see a statistically significant effect. But what that doesn't say is, do we actually ever observe anywhere that has high property tax revenue and high violent crime? That we don't know. So we want to go back to the data to check that, right? But this is a great way to visualize regression predictions, right? Here, what can we see from this plot? Let's describe what we see here. Other than pretty rainbows. As property tax collections go up, what happens to police spending? Very clear there, right? Super clear relationship. We see a sharp increase in police spending for property taxes. For higher property taxes, we see, in general, places with high segregation spend a bit more on police than places with low segregation, but it's not a clear gap between the two, right? The fact that we have a lot of overlap here suggests that, yeah, there's a difference, but it's maybe not a huge one. Those are default.
Very nice.
Yeah, ggplot will make good default choices for you most of the time. I did put an alpha on here to allow transparency so we can see the zone of overlap. But this is a great way to visualize regression results. So I strongly recommend when you're pulling your models together to think about what's my core question? My core question is, do places with higher levels of property tax collection spend more on policing? And based on this, I can see that that's clearly true. I can say that, in general, places with about $500 per person in property tax collection are spending, in this range when they're in a low crime zone and also when they're in a high crime zone, regardless of segregation. But then I can kind of narrow my interval a little bit, conditional on segregation. That's the range in general. That's where we expect on average them to fall. So as a predictive model, this can be incredibly useful. Okay, but these results are not the causal effect of segregation or poverty or property taxes on police spending. right? They are not the causal effect. We have not made any effort to address unmeasured confounders of property taxes, which there are a lot. We haven't made any effort to deal with collinearity of the predictors. There is collinearity in the predictors, but they could still be perfectly valid predictions. And in this case, they probably are. They probably fit the data quite well. Why don't we check that actually? So we have one way we could check that. What's the data called? Budgets. And then we're going to add in a scatter plot with the observed data here. Sorry, got to remind myself what these are called. All right. It would take a little more work to get this working, but we could, in theory, scatter plot over this with the observed data to just get a sense of like how well are the observed points actually falling in this range, right? And that would be a good next step. Okay, so we are approaching the end. What these do, so they don't give us causal estimates, but they do give us information on the direction, magnitude, and precision of the joint relationships across the variables in the observed data, right? They tell us about conditional means, right? They don't tell us about causal effects, but they do tell us about conditional means. And that can be helpful. Higher property taxes do tend to mean higher police spending. So we can say with a high degree of certainty, places with higher property tax revenue spend more on police. I can't tell you that if a place increases its property tax revenue, it will increase its police spending. I cannot tell you that. But I can tell you that if a place has high property taxes, it's probably going to spend more on police than a place with low property taxes. I can definitely tell you that. So we can still learn a lot from predictive models, right? We just don't necessarily learn the precise impact of a change, right? That's something we need to design for. The confidence intervals provide us with information about the precision of those estimated relationships. So in this case, we don't have a ton of certainty in the segregation impact, right? Like if I were to tell you 2 counties, same property tax values, one's high segregation, one's low segregation. I can say, you know, on average, the high segregation county is going to spend a little more on police, but there's a good chance that they'll spend the same, right? On average, it's going to be a bit higher, but there's also a lot of overlap here. So they could spend about the same amount, right? The intervals are different, but they overlap with each other. So we would want to be conservative in interpreting the impact of segregation, or not impact, but if we had 2 counties, one was high segregation, low segregation, and making that guess. But the interval on spending, like we can think about the interval on a slow spending county here versus the interval on a high spending county here, and they do not overlap with each other at all. So we have very clear information that based on those confidence intervals, that spending really is associated with differences. I'm sorry, taxes are really associated with differences in spending. But don't overinterpret on beta, right? Typically, when we're looking at betas, what I don't want you to do when you have a beta to interpret is to say the relationship between log property tax and log police spending is 0.027. I want you to say it's positive, right? And then think about the scale, right? What's a 1 increase on log property tax revenue? I'm not clear if that's big or small based on this, but when I translate it to the scale of the outcome itself, it actually looks quite large. It looks like it's a big positive effect, big positive relationship. See, I catch myself doing it because it's like so ingrained in how we do this. You have to catch yourself on it. It's not an effect, but there's a very clear positive relationship here, a large positive association. Okay. And we want to think about how predictors move together in the real world to constrain our predictions and make them more reasonable because our predictors are correlated with each other. For example, segregation, as I've said like a dozen times now, segregation and property taxes or crime and property taxes are correlated with each other. So we may want to think about whether it makes sense to even predict a high income county with high violent crime. Is that something we ever expect to see? Yes or no, right? And so we can think about the actual patterns of the data to structure where we want to predict over. Sometimes if we just predict over everything that's possible, we might predict nonsense, right? We might predict something that is theoretically possible but would never occur in reality. So we've got to be careful about that. Okay, homework 11. Just because I want you to do a little more regression practice at the end of the semester, I'll give you all 2 weeks to complete it. So you can have until basically, I'll tell you the date on Slack, but I'll give you like until 3 days before the grades are due. So you'll have a couple weeks to submit it. But we're going to do another study replication. It's replicating a paper from the American Sociological Review that looks at the penalty of earnings for motherhood. So it looks at how much less money do mothers earn than non-mothers, right? And so we're going to ask, this is a kind of common question in a field called stratification economics, right? So we want to think about causes of inequality in earnings, right? And it's well known that women who have children earn less than women who don't have children. And so we want to start to think about why that might be the case. So we're going to use this large data set to estimate wage. Here is the outcome of interest. And I'm going to ask you to compute log wage, look at correlations across variables. Oops, gave you a solution. Oh, I gave you that because it's a weird function. That's okay. And then build out a model of logarithm of wages based on number of children, based on a few other variables, and think about interpreting what all this means together. Now, this is a study that did actually claim to make causal inferences based on a particular design. We're not going to push it that far. It gets a bit technical to add those in. If you ever see the language of fixed effects in here, I introduce it here, a fixed effects model. That just means adding in categorical predictors into your model, right? So factor year, then treats year as a separate intercept for each year. Factor region treats that as a separate intercept for each region. And that is called a fixed effects model when we introduce lots of additional intercepts into our model. But don't worry too much about that. I think you all can handle this, but again, the Slack channel will be open. If you haven't, completing the course eval is helpful for me. If you have gotten the link, I'll post it in Slack if you haven't seen it. And otherwise, this has been, for me, I think a much better semester than last semester because we're actually in person, and it's nice to be in person again. And y'all have been great. And I do want to thank you for your patience on the